yesterday. Not something I think about. Okay, so today in section 2.5, we're going to do variation. I did send out the lecture notes. I'm hoping you had a chance to at least look at them. If not, I'm going to read the problems to you so you'll have them anyway. But there are three main types of variation. This will make a lot more sense once we start into it, what we mean by the word variation. So the first type is called direct. Variation. And what that really means is that y, and we're going to pick on x and y just because we're familiar with them. Varies directly with x. So an example of direct variation would be something along the line. If x represents the number of hours that you work and y represents your salary, then it makes sense that as you work more hours, you get more money. So that's an example of a direct variation. In terms of an equation, we're going to write something that looks like this. We're going to say y equals k times x. Now that k just appeared out of the blue, and I understand that. I consider it to be kind of a fudge factor. So this might be like your hourly rate. So if you're making $12.75 and you multiply it by the number of hours, you figure out how much money you're making. It's called the constant of proportionality. That's a big title. Constant of proportionality. We're just going to call it our constant. It's also sometimes called the variation constant, depending on the book. And it simply is, like I said, like your hourly rate. It's kind of the slope when you think about this from a linear point of view. It's the slope of that line. And that's a direct variation. From a graphing point of view, it's going to look something like this. So if this is x and this is y, as x is getting bigger and bigger and bigger, well, so is y. So in other words, if you work more hours, your pay is getting bigger and bigger and bigger. So it's doing this kind of thing. So we're going to say as x increases, y also increases. And that's a direct variation. And that's why it's called direct, because as one is going up, the other is also going up. That's my favorite kind of variation because things are both increasing, which is always a good thing. Okay, have you seen direct variation before?
Yes.
Okay.
Yeah.
That's a good sign. Should be an easy section then. Okay, type 2 is called indirect. Or another word is inverse variation. So indirect or inverse, they mean the same thing. Your book uses both terms, so you'll see both of them in the homework. And this time we're going to say that y varies indirectly with x. So you'll actually say that word directly in the sentence, indirect. What that means as an equation is that y equals k over x. So I'm still using the same k, it's the constant of proportionality, but where I've placed x is in a different location. You'll notice that because it says indirects, I'm going to put the x under the k. Now what happens with this guy is it's simply saying that as x increases, what's happening to y? So think about this in terms of fractions. Ignore the k for a minute, just make it a 1 in your brain. But as a fraction, if that denominator is getting bigger and bigger and bigger, so a 2, a 3, a 4, so 1/2, 1/3, 1/4. Well, as the bottom number gets bigger and bigger and bigger, the y is getting smaller and smaller and smaller. So as x increases, y decreases. So they're going in the opposite directions. As one is going up, the other is going down. And that's why it's considered to be an inverse or indirect relation. From a graphing point of view, it would look something like this. It's going to be going down. It does not have to be a line. It can be a curve. So don't let me mislead you in terms of it. It simply means that as x gets bigger and bigger and bigger, the values for y are going down. So an example of that, let's see, what would be an example of that? Can anybody think of something where as it gets bigger and bigger and bigger, which, yeah, like the tax brackets, right?
Gravity.
Yeah, gravity, right? As you get further from the Earth, so as X gets bigger and bigger and bigger, the value for gravity gets smaller and smaller and smaller. Atmospheric air pressure would be the same way, right? As you go up in an airplane, the amount of air that is breathable or pressing down on you is getting smaller and smaller and smaller. Both good examples. Physics comes in handy here. Our third type of variation is called joint or jointly variation. So joint variation. And what's going to happen here is instead of just using a single variable x, we'll pull in other variables. So we could say something like y varies jointly with x and z. So we see the word jointly in there for the first time. So when I go to write my equation that represents this statement, I'll still have y equal k. Because it doesn't say anything about the relationship between x and z, we always assume it's a product. So we're just going to do x times z. So again, we're going to assume that it's a product, which means to multiply for joint variations. Unless it says something set differently, that's true. And for the most time, if they want you to add them, they would say the sum. If they want you to put one in the numerator and one in the denominator, they'll use it as jointly with a direct and an indirect. And we'll do examples of all of these. So in terms of pictures, if x and z are getting bigger, then y is getting bigger. If x and z are getting smaller, then y would also be getting smaller. It's just getting bigger at a faster rate because it's a product. So, and that's a joint variation. So those are the three basic types. So direct, indirect, and joint. And then what we're going to do is we're going to start off really easy, or what I consider to be easy. We're going to work on just writing the equations and finding the values for k. So what the directions are going to say is to write, so this is example 1 on my handout. We're going to write a general formula to describe each variation. So part A says y or v varies directly with t. And then it goes on to tell me that t or b equals 16 when t equals 2. So they give me a little bit more information than when we were talking about the types. So our first step here is going to be to come in and just write the equation. So we're going to write an equation, and that's based on the type of variation. So because our initial problem says the word directly, I know that when I go to write it, I'm going to write v, and then I'm immediately going to put in my equal sign, and then my k. So anytime you write the equal, put the k directly after it. K will always be written next to that equal sign. And because it says directly, we know to put the t right next to the k. So there's our equation of variation. The problem is we need to figure out k. So step 2 is to determine or find k using the given values. So for us, they told us that v was 16. So I'm going to replace my v with the 16. That's going to be equal to k, which we're going to solve for. And we know that t is 2. So I have k times 2. I'm just using parentheses to try and differentiate things. And now we're just going to solve for k. We'll divide both sides by 2. And sure enough, we see that k is equal to 8. So then our third step is to plug that back into the equation. So step 3. replace k. So then we now have an equation, a variation, where v is equal to 8 times t. So since we got k to be 8, we just plug it in and there it is. And that's the final answer for this kind of problem. So they just want you to come up with a variation equation that describes those specific values that they gave you. So, any comments or questions? These are my favorite application problems because for the most part, you write them as you read them. Let's do a couple more of those just for practice. Part B on that example. It says that F varies inversely with the square root of D. Nope, R, sorry. I should put my reading glasses on. Sometimes why I wear them. And F equals 4 when R equals 9. So again, our first step, we're just going to write the equation. So we start off with F. We're going to put the equal, and then we'll put the K. Now, in a minute, they're going to come out of these simple ones and actually go to true application problems. So varies is my verb, and the inversely is telling me how to put things after the K. So because it says inversely, I know anything following that is going to go in the denominator. So I end up with the square root of R underneath. So varies is the equal sign. I immediately put the K, and it inversely tells me to put the root of R underneath it. Then we'll plug in our set of numbers. So now we know that F is 4 when R is 9. So that would be the square root of 9. Now we just have to solve for K. So the square root of 9 is 3. We'll multiply both sides by 3. So we end up with K equal to 12. So then the final answer is going to be F is equal to 12 over the square root of R. So ideally, if you now give me a value for R, I can tell you a value for F. Or if you give me a value for F, I can tell you what R is. So comments or questions about that one?
I'm okay.
Good. Thank you. Okay, still with the same set of directions. Part C on that problem says T varies jointly with the cube root of X. So cube root of X and the square of D. So the square of D would be D squared. They then go on to tell me that T is equal to 18. X is 8. And D is 3. So 18, 8, and 3 are the given pieces of information. Okay. And again, we know that jointly means to use a product. So for us, we're going to start off with T equals and then K. So varies is the equal sign. We immediately put a K. Jointly means a product. So now we'll put the cubed root of X. And then that would be times D squared. So on the right side, I just have K times the cubed root of X times D squared. Okay, let's plug our numbers in to see if we can figure out what K is. So T is 18. K times the cubed root of X, which was an 8, times D squared, which is 3 squared. Let's clean up that right side. Cubed root of 8 is 2. 3 squared is 9. So I end up with 18 equal to 18K. So when I divide out the 18, we'll get K is equal to 1. Not very exciting for a constant, but there it is. So then our equation then becomes T is equal to 1. I'm going to write it in. You don't need to write it in, but just so that we know where it went. The cubed root of X times D squared. It doesn't really matter in what order you write those. I'm just doing it in the order it was given. So there's a joint variation. So we've done a direct, we've done an indirect or inverse, and we've also done a joint. Okay, let's do one more of the basic ones, just to show you that they can kind of vary. No pun intended. Part D on that problem says the square of T varies And it says jointly, that is a typo. It varies directly. So again, there's a typo there if you printed them out with the cube of A. And inversely with the square of D. So that would be D squared. Then goes on to tell me that T equals 2 when A equals 2 and D equals 4. Okay, so T varies, the square of T varies directly with the cube of A and inversely with the square of D. Making sure I wrote that correctly. Okay, let's plug our numbers, or let's write our equation, sorry. So we're going to start off this time with T squared. So the reason we did this one is so that we can see that sometimes the left side will have stuff on it too. That's going to be equal to K. Now the first thing I read from left to right is the word direct. So that tells me that the A cubed is going to go right next to the K. The next thing we see after the and is inversely. So that means I now go to the denominator and write anything else in the denominator. That would be T squared. So there's our equation. Now we can plug our numbers in. So T was 2, that'd be 2 squared is equal to K times, A is 2 also, but we need to cube it, all over D squared, that would be 4 squared. Well, that's 4 equals K, 2 cubed is 8, 4 squared is 16. I'm going to go ahead and simplify this side before I worry about going across the equal sign. So 8 and 16 will both divide by 8, so that's really going to give me K over 2. And then we'll just multiply both sides by 2 to clean it up from there. And we end up with K equal 8. Just double checking my arithmetic, looks good. So then our equation of variation is going to be T squared is equal to K, A cubed, over D squared. So your homework will start off with you doing some of these basic ones where all you're doing is just finding a value for K. Well, you're writing an equation, finding a value for K, and then plugging it back in. Oops. Plugging it back in. There's our 8. So, sorry about that. Any comments about the basic ones? Okay, we'll move on then. And we'll start doing what I call the full-blown problems where we have to do all the steps. So these actually look like word problems now. So example 2, and I'm not going to write it, I'm just going to read it. Tells me that the period of a pendulum is the time required for one oscillation. So a pendulum is something that swings back and forth like a swing, a kid on a swing. So one oscillation is where you start on one side, swing out, and swing back, so you're ending up in the same spot. The period of a simple pendulum in seconds varies directly with the square root of its length. A pendulum is 32 centimeters long and completes one oscillation in 6.28 seconds. Write an equation that relates the quantities. So they put a lot more words in. The first thing we're going to do is we're going to come in and define our variables. So our first step is to define the variables. We got to figure out what we need. Okay. So it says the period of a pendulum. So we need something for period. I'm going to use a capital P. For me, that stands for period. Of a simple pendulum varies directly with the square root of its length. So I need something for length. I'll use an L. And again, I'll use a script L because if I use just this for an L, it looks like a 1. So I'll use a cursive looking L. Okay, so that's all we need. We only have 2 variables. There they are. So our next step is to write our equation. Okay, so they told me that in that second sentence, the period varies directly. So I'm going to write P equals K, and that's coming from the varies directly. The square root of its length. So square root of L, and there's our equation. Good. Okay. Step 3, we're going to come in and then put the numbers into it. So we know the pendulum is 32 centimeters long. So that would be our length. And we know it takes 6.28 seconds to swing back and forth. And that's going to let us find K. So K is going to be equal to 6.28 divided by the square root of 32. I'm going to go ahead and take that to a decimal. It is a word problem. Take it to a decimal. So If you take 6 and divide it by the square root of 32, you end up with 1.11 as your answer. So then step 4 is to rewrite our equation. So our equation would then be the period is equal to 1.11 times the square root of L. So now if you give me the length, I can tell you how long it's going to take that period, that pendulum to swing out and back. There it is. Woohoo! So a few more words thrown in, but still the same basic process. All we had to do in the beginning was to find my letters. Because you're doing the online homework, I don't think that's going to be a big issue. I think they're going to give you what letters to use. So, comments or questions?
Makes sense.
Yay! Thank you. Okay, example 3 talks about a string vibrating. So this would be like a string on a guitar or a string on a piano. When it vibrates, the little hammer hits it. So the rate of vibration of a string under constant tension, so again, I have a string and it's under tension, varies inversely with the length of the string. If a string is 48 inches long and vibrates 256 times per second, what's the length of a string that vibrates 576 times per second? Okay, so let's walk through the steps again. The first thing we're going to do is come in and define some variables. So it says the rate of vibration of a string. So I need a letter for all of that. Because it says rate of vibration, I'm going to use R for rate. So R is going to be my rate of vibration. So how fast is that string bouncing back and forth when I pluck it? Varies inversely with the length of the string. I'll use that L again for the length of the string. Again, what letters you pick doesn't matter as long as you're letting us know what letters you're picking. Okay, we'll write our equation. So we know that the rate of vibration, and the sentence reads, the rate of vibration varies inversely. So I see my K, and because it says inverse, we'll put the L under the K with the length of the string. So there's our beginning equation. If the string is 48 inches long and vibrates 256 times per second. So I don't know K, but I do know that it is a 48-inch long string. And that means that the 256 has to be my R over on this side. And we'll solve for K. So let's just multiply both sides by the 48. And when we do that, we're going to get a fairly large number for K. It comes out to be 12,288. In the mathematical world, we don't care about the units on K. In both physics and chemistry, you do care about the units on K, but for us, we tend to ignore units in mathematics until the end. So that's 12,288. Okay, what we now know is that the rate of vibration is equal to that 12,288 over L. Now this problem has an additional step because it then says, what is the length of a string that vibrates 576 times a second? So now we're going to come back in, we're going to replace R with the 576, and we need to find L. And there's the final step. So now we're actually using the equation of variation for another set of circumstances. So 576 is equal to 12,288 all over L, and we need to solve this for L. How are we going to solve that for L? Have you got a suggestion?
Multiply by L?
Yep, let's clear the fraction. So we'll multiply both sides by L. That's going to give me 576L equals the 1,288. And then divide by the 576. So L is equal to the 12,288 divided by 576, and I got that to be 21.33 inches. Okay, follow the directions carefully on the homework. They're going to tell you how many decimal places to use. So I did the nearest hundredth, but they might use nearest tenth or nearest hundredth. I don't know. You'll have to follow directions, so be careful. Okay, any comments about that one? That's a full-blown problem. All the parts are there. We have used this one on a final exam before, so we consider this to be a fairly typical problem. Okay, our next problem I really like, only because the wind blows so much in the springtime here. that it really reminds me of those gusty winds that we just had the other day, in fact. Okay, so example 4 says, the force exerted by the wind on a plane surface. So we're talking about the force of the wind against your windows or the side of your house. Varies jointly with the area of the surface, how big the window is, and the square of the velocity of the wind, which makes sense, right? So how much force is dependent upon how fast that wind is blowing. If the force on an area of 20 square feet is 11 pounds when the velocity is 22 miles an hour, find the force on a surface of 47.125 square feet when the wind velocity is 36.5 miles per hour. So that's a lot of information thrown at you. Let's define some variables. So we need a force. So I'm going to use F for the force. It goes on to say that that's going to vary jointly with the area. So I'll use A for area. And the square of the velocity. So I'm going to use V for velocity. Now, just to help organize things, I'm going to put the numbers that they give us. So they tell me that the force on an area of 20 square feet is 11 pounds when it's blowing at 22 miles an hour. It then goes on to tell me to ask me to find the force when we're on an area that's 47.125 square feet and the wind is 36.5 miles an hour. So, okay, so that's just the data that they're giving us. Okay, we've defined our variables. Let's come in and write our basic equation. So it tells me that the force varies jointly, so that's F equals K. Then tells me with the area of the surface, that would be times A, and the square of the velocity of the wind. So then we'll put a V squared in there. So the force varies jointly with this area of the window and the square of the velocity of the wind. So there's our equation. Almost spells out a word, cave. Okay, let's plug the numbers in and see if we can find K. So we're going to use this first set of numbers that are sitting right here to find K. So the force is 11. Don't know K. We know the area is 20. And we know the wind is blowing at 22 miles per hour. So, okay, on the right-hand side, let's figure out what all that is. For some reason, I don't have that individually. Sometimes when I key these up, I tend to not put all the steps in. So I'm going to take 20 times 22 squared, and that gives me 9680 times K, and then we'll just divide by the 9680. And we end up with K equal to, so 11 divided by 0.001136. So I'm going to carry 4 digits on this just to make sure that I've got the answer that they're looking for. Don't round this too quickly. If you want to have the calculator carry all the decimals, that's probably a better idea. It makes it awkward to write them. So right now we know that our force is going to be equal to 0.001136 AV squared. So now if you give me another surface area and wind speed, I can tell you what the force on the window is. So now we'll do the second part of this. So now we're going to come in and use that second set of data to figure out what the force on that window is. So in this case, the force would be equal to 0.00136. The area is now is 47.125. That's a big picture window on your house. That's almost what, a 6 by 8 foot window would be 48. So that's a big window. That wind is blowing along at 36.5 miles per hour, and we have to square that. So at this point, it's just straight plug and chug. You just take it to your calculator, multiply it all out, and you should end up with 71.32 miles per hour. I'm sorry, 71.32. This is a force, and I have to figure out what units are on this in the final answer. So I go back and read through the problem, and in an earlier sentence it says the force is 11 pounds. So this force over here was 11 pounds. So I know that this is going to be in terms of pounds. Okay, so what is this really saying about this? Well, what this is saying is if you have a big picture window, we call them, in the front of your house, it's a 6 by 8 foot window. That wind is blowing or striking that window at 36 miles an hour. That's the same thing as a 70-pound person standing on that window exerting a force on it, which is why your windows are now double paned to help with that issue in terms of the wind. So Any comments or questions about the wind problem? I like the wind problem.
I'm good.
Okay, one more and we'll call it good for the day. We're going to do one that's really similar to a homework problem. I don't think any of you are business people, but it's great for the business people. The last example, example 5, says that the cost of roasted almonds varies directly with the number of pounds purchased, which should make sense, right? You go, you're going to buy some mixed nuts or some roasted almonds in this case. The more you buy, the pricier it is. So if the cost is $23.75 when 5 pounds are purchased, find a linear equation that relates the cost to the number of pounds, then find the cost when 3.5 pounds are purchased. Okay, so we need some variables again. I'm always going to start here. So the cost, I'm just going to use C for cost of the almonds. It varies directly with the number of pounds purchased. So I'm going to use P for pound. No, actually, I'm going to use W for weight. It's only because P for pounds just sounds weird to me. So we'll use W for weight. And it is given in pounds. Okay, I'm going to do the same thing I did last time. I'm just going to put the numbers down. They tell me the cost is $23.75 when I purchase 5 pounds of roasted almonds. So they then want me to find the cost when I purchase 3.5 pounds. So what's the cost when we purchase 3.5 pounds? So there's the information. Let's go write our beginning equation. I'll go back to what it says. It says that the cost varies directly with the number of pounds purchased. So because it says varies directly, we're going to put the weight right next to the K. We can then plug in the first set of information to figure out what K is. So we know that it was $23.75 when we purchased 5 pounds. So that would be K times 5. We'll just divide both sides by 5. And K comes out to be 4.75. So in terms of the earlier application problems we did at the end of chapter 1, this would be the cost per pound. So we know those roasted almonds cost $4.75 a pound. So our equation is C equals 4.75 W. That right there is the linear equation they're talking about. How do I know it's a linear equation? Because there are no exponents. So that makes it a linear equation. And the W is not in the denominator, so it's definitely a line. We can now figure out how much it's going to cost when we purchase 3.5 pounds. So we're going to take C is 4.75, the cost per pound, times the number of pounds. So times that 3.5 pounds. And you should end up with $16. And because we're dealing with money, we'll round it to 2 decimals, $16.68. So if you purchase only 3.5 pounds, it's only going to cost you $16.68. Any question on our variation problems? Pretty straightforward. I hope it doesn't take too long tonight. Okay, so the plan for tomorrow then, you have a review that's due on Saturday for the exam that's due on Sunday. We're going to do some review questions tomorrow in preparation for you doing that review as your homework. Any other comments or questions?
I'm good.
Thank you.
Okay, we're all good? Okay, well, have a great day. Enjoy it. Enjoy that 100 degrees, Christina.
Thank you.
Bye-bye. We'll see you tomorrow.
See ya.
Bye.